Okay, so today I figure I'd go actually into something a little bit more interesting. Again, there's methods behind my madness here, but I want to go over a review of what we've done so far, because oftentimes what we study in quantum field theory and quantum mechanics and physics is we oftentimes get lost in the weeds, get lost in the equations, and we have a hard time figuring out exactly what's what in the equations and what exactly we're doing. And quantum field theory is notorious for this, right? We have so many variables that we're trying to keep track of, and we often lose sight of the big picture. So let's do a review. So what we've been talking about so far is we've been talking about states. We've been talking about how particles can be represented as states. Those were those sort of the 5 postulates that we've covered. And then we also covered Hamiltonians, the Schrödinger equation. So let's go over this. We covered states. We covered states, and these states they can be represented as wave functions. These things can be functions of space and time, or they can be represented as vectors. So this is the function notation, this is the vector notation. Okay, and then things operate on these, right? So these are operators. So operators operate on states. So operators operate on states to give observables, right? So when they operate on these states, and they give us observables. Observables. And so for every operator, there's a set of observables. I'll rewrite. That looks a little bit messy. Observables. Okay. And this here, our set of observables. Actually, I'll be much more precise here. Let's do a set of observables. The reason I say set of observables because this notion right here is a spectrum, right? This is a spectrum. So I can do I could take a spectrum. These are the spectrum of possible states, right? The spectrum. I'll just say spectrum for right now. So operators operate on states, right? And they give us a set of observables, and this defines the spectrum of states that are associated with spectrum of states associated with the operator, the specific operator. Specific operator. All right. I'm trying to be precise in my language here because we want to understand this well, right? We start with states. Operators act on states, so it can operate on these guys, or it can operate. This is in the continuous case, right? So this is the continuous case. And then this here, it can operate on these guys. In this case, this would be the discrete case. Right? And so we took a look at the form of some of these operators, right? We took a look at the we took a look at this sort of nabla operator, and this was synonymous with finding the momentum spectrum, or the momentum states. So momentum we also took a look at the DDT operator, right? DDT operator is synonymous with the energy, right? The energy of a state, right? All right, so this right here again. This is the this is a derivative with respect to space, right? And then we have just this here. This is just merely multiplying our state by some value. This gives us position. And I sort of talked about operators as being these things that reach into this infinite dimensional space, right? We can't really draw infinite dimensional space, but we have this operator that reaches into the infinite dimensional space, and the output is a spectrum of the subsets, the infinite subsets. Could be infinite. Sometimes they're not infinite, but the subsets of all the possible observables that are associated with these operators, right? So we get observables. And this is our infinity. We can say that this is our Hilbert space also. This is a Hilbert space. Right, and then we talked about this operator here. This is our famous Schrödinger equation operator, right? We define this as h bar over I d squared dt squared plus our this is our Hamiltonian operator. So our Hamiltonian operator. And then from the Hamiltonian operator, we went and we said we can define these guys, these creation and annihilation operators. Okay, usually we don't have the minus there for the creation, but again, this is a creation and annihilation operators. And these create and annihilate particles at specific quantized frequencies. So creation and annihilation at specific frequencies. And these things these come out of the Schrödinger equation. Right? And then now here's where, so this is the broad overview of what we've done so far. We went into some more details, but I'm not going to go into the details again. What I do want to do though is I want to sort of get our feet wet a little bit with perhaps not much more, but some more advanced concepts. Right? So towards the latter end of, I think, my last video, I said, well, these operators right here, right, these creation and annihilation operators, heck, even the Hamiltonian operator, nothing is really stopping us from saying that these things are functions of space and time, right? They're operators, right? But again, they can be functions of space and time, right? So we can have a dagger and A, And these things can be functions of space and time. Right? So you give me some location in space. So here's this picture again. So this is our manifold that defines our space. Give me some location in space, and I could tell you to what degree there is creation and annihilation operators in here. Right? So again, we have this is our function of space. We have x, y dimensions, and then our z and our t dimensions are suppressed, right? Because I can't really, I could try to draw a z dimension, right? Maybe it looks like this. Right? It could be a curved space-time, right? But again, so these guys, these creation and annihilation operators, these things are functions of space and time, right? There's more stuff at one point in here. Like we said, there was, we have, there's more stuff in it. I'm just saying, for right now, I just want to focus on these creation and annihilation operators. Again, so what's the consequence of this? Well, we've sort of taken a look at these guys, right? We've taken a look at these guys and we've said, right, so I can draw some sort of maybe Jablonski diagram again. And I'll just have a two-level system. And this two-level system, in this two-level system, I can create a particle to show up at the higher energy level, like this maybe, and then I can annihilate a particle and I can lower back down. So these are raising and lower operators, right? So we raise up and then we go down. This is our lowering operator. So we create particle, we go up to this state, we annihilate particle, we go down to, we take that particle back down to the ground state. Okay, so what does this mean for us? This means that if now we have these things as functions of space and time, okay, well, how does this picture change? Well, this picture changes, right? So these things are functions of space and time. We could think of maybe these little Jablonski diagrams in this one region, right? I'll draw this again, maybe zoomed up on one particular area. So we have our space-time, and at one area here we have this little Jablonski diagram. This is kind of a weird way of drawing this, but this is at one particular region. We can induce creation. We have creation here, right? This is kind of small, but again, so this was creation at point P, for example, and time T1. Actually, so instead of P, I'll put X1. So this was creation at time, or at point X1, and at time T1. Right. Consequent further creation particles, or further creation operators, could occur not just here, but it could occur here. Again, there's nothing stopping us from saying, well, another A dagger or an A not dagger, there's nothing stopping us from saying that it necessarily has to happen at this point, right? It could happen over here, right? And so So we're going up to the second energy level, n equals 2, right? This is getting a little bit cramped. N equals, so we went from n equals 1 here to n equals 2 here. So this is kind of a weird picture. But that's sort of the consequence of this, right? So we have these creation and annihilation operators. And right immediately when we start thinking about them as functions of space and time, we begin to understand how quantum field theory works. Now, why? Because why is this quantum? Why is it called quantum field theory? Why is it called quantum field theory? Well, the quantum means that we're raising by integer numbers. The field, right here, means that our operators, the operators that are doing this, are functions of space and time. This is a field, right? This is a field that, and this is a field as well. Whenever we have these arguments in here, functions of space and time, this is a field, right? Okay, and so this is kind of why it's called quantum field theory, right? The quantum part is we have quantized energy levels, right? We have n, then we have n plus 1 state, we have n plus 2. Right? These are our quantized states. The field means that our operators are functions of space and time. All right, so I can't really emphasize this point enough, where we now want to consider three-dimensional space, and within each point of our three-dimensional space, we have an operator of space and time. And so we have a suppressed time axis component here as well. Okay. All right. So let's go a little bit deeper into this concept, because this is actually pretty interesting. So we know, perhaps we don't know, but I can tell you right now that if you study GR, right? If you study GR, that space-time can be curved, right? And you don't even necessarily have to understand, you don't really even have to know this by studying GR. Einstein and his ideas were popular back then as they are back now, and a lot of his theories have been proven true. So we know that there's a curvature to space-time. Okay. Now, here, this is interesting. This actually gets pretty interesting here, because we could have flat space-time. Here's our flat space-time. Here's as flat as I can make it. That's not flat. So this is our sort of our flat dimensional space-time. And across this space-time, we have these little raising operators. We have some raising operators here. Actually, I'll do it like this. We'll say that our raising operators, I'll put them off to the side here, just give a legend. We can say that, we'll say our raising operators are red and our lowering operators are blue. Right? So with this picture in mind, suppose we have some raising operators at one point in space. So for every point in space, there's some raising operators. For every, there might be less over here. There might be a ton over here. There might be one or two over here, and there might be only just one right here. And then maybe a bunch right here as well. we have these raising and lowering operators, and they exist at every point in space and time. So here's, I'll do the blue ones. So, and this is what we are calling a field. All right, this, we have different degrees of the existence of these raising and lowering operators at different points in space-time. If, here's the big if right here, if we transition from, this is flat space, this is flat space-time, and this is given by our Minkowski metric. If we undergo, if we have a metric now, if we transfer from a flat space-time to a curved space-time, here's some curved space-time. So this is curved. If we make this transfer, and I'll try my best to make this three-dimensional to some extent, and we don't know exactly what the curvature looks like. It might look something like this. And I'll try to make this as accurate as I possibly can. So 1, 2, 3, 4, 5. So there was 5 at this one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 here. Remember, this is just a picture to sort of get us to kind of understand what's going on. I don't want you to take this picture totally for heart, because there are some aspects that some things that this picture won't completely be able to cover, because quantum field theory is such a complex topic to understand. A single picture doesn't really do us justice, right? But I'll try to do this, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And there was 2 over here. And then 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And there was only 2 here. And then only 2 here. Or 1 there. And then I'll put our annihilation operators in here as well. So there's 3 here, 3 here, at this location in space and time, this location in space and time, and then there's 3 right there, and it looks like there's 4 at this location space-time, and 1 right there. Okay. So the density doesn't change. The functions, these functions don't change. Right? So as we go from here to here, a dagger of x and t is no different than a dagger and x of t here. We sort of reparameterized our flat spacetime to model that of a curved spacetime, but the creation and annihilation operators, the number of them changes. Their eigenvalues could depend on the curvature of spacetime, but if they don't, if these guys don't change, again, these guys also don't change. These guys also don't change. These guys are operators, and their eigenvalues, their eigenvalues don't change as we transition from flat space to curved space. And so, again, this picture isn't total. I'm not going to say this picture is totally correct, right? But it does sort of kind of maybe give us some intuition behind how we can begin to think of topological quantum field theory. Right, so topological, this is an interesting word right here because oftentimes we are interested in geometrical quantum field theory. Geometrical means that distances matter. If we change the distances, or if we change the metric, then things change, right? So if the metric changes, in this case we have G mu nu, then things matter. In other words, if we make this change, but nothing happens, like sort of in this picture, if we make this change, but nothing happens, then we are dealing with a topological quantum field theory. And this enables us to consider multiple spacetimes, right? This enables us to consider multiple spacetimes in which the observables that are associated with these operators don't change, right? This is why this is what makes a quantum field theory a topological field theory. A quantum field theory, it is a topological one if our decision on the metric doesn't change anything, right? So we can have a Minkowski metric. We can have the Schwarzschild metric. We can have the Ernst metric. We can have the Kerr metric. If we use these metrics to do our quantum mechanics on, and nothing changes, there's no change in our quantum mechanics or in the measurements of our quantum mechanics, then we are ultimately dealing with a topological quantum field theory. A geometrical quantum field theory means that the space-time does matter, right? If the Lagrangian contains our metric, then if the Lagrangian contains our metric, that means it is not a topological quantum field theory. If it does contain the metric, that means if it does not contain the metric, that means it is a topological quantum field theory. So the end point here, the end point is if G mu nu, then geometric. If no G mu nu, that's a little bit too confusing. If our let's see here. So if G mu nu matters, then not topological field, not a topological theory. Right, this is if G mu nu matters, or if the metric matters, then this is not a topological field theory, right? And I will come back to this, right? It's going to take a couple of videos, but it's going to take a couple of videos to get back to this point, but I sort of want to motivate it, right? I want to be able to consider these different types of operators, because again, we're going to come across operators that look like this, right? And these are bosonic operators, or bosonic creation and annihilation operators. These things are also functions of space and time, right? These things are also functions of space and time. And we can integrate over all space and time, and we can figure out what these what the values of these are over regions of space and time. And we actually, if you study, I didn't know I had this whole I didn't know I had this whole other part to my slide here. But if we actually study quantum field theory in depth, which is what we're going to keep on doing for this series, we will be able to see that we are going to run into problems where we're integrating over infinite domains of space to figure out the values of these functions that hold these operators. So we're going to have to circumvent that as well, right? But what are we going to cover within the next few lectures here? I want to go over some important concepts that are sort of, they're not taught very well, I don't think. Green's functions. Green's functions. I'm trying to think of a way right now. I'm currently trying to think of a way on how I want to go about teaching Green's functions, because these things are super, super, super important for every operator, right? So for every operator, we're going to have a Green's function. So we're going to have a Green's function. The Green's function is going to tell us a lot about how we get from state A, or from state 1 to state 2, or perhaps from state initial to state final, right? These Green's functions are going to, they're known as propagators, right? So for every operator, there's a propagator. So this is our operator. There's a propagator, right? I want to go over the Klein-Gordon equation, right? This is sort of where we start the Klein-Gordon equation. We actually haven't gone over the Klein-Gordon equation yet. We've been going over a bunch of details behind the postulates of quantum mechanics and behind the creation annihilation operators. But this right here is usually where quantum field theory starts, by considering the Klein-Gordon equation. But we're just starting to get into this. We're just starting to get into this now. But yeah, so I want to go over the Green's functions. I want to go over the Klein-Gordon equation, and then eventually this is going to take us to the Dirac equation. And I'm still not totally sure on the order I want to do this. Because there's different angles we can go about studying this kind of stuff. But sort of as before I leave you here, there's this idea that the Klein-Gordon equation describes bosons, and the Dirac equation describes fermions. Bosons include things like photons, and fermions include things like electrons. And we're going to be able to develop now. This is sort of beginning to develop QED, right? Quantum electrodynamics, right? So we're good. So we've been talking about field theories. We've been talking about quantum field theory. And now I want to start talking a little bit about QED, and again the math, or the Green's functions, that are involved in these types of calculations. So we can actually be able to do calculations, make measurements. So with that being said, I will see you guys in the next one. Thanks.